kitchen with Carla. Someone's in the kitchen, I know. Hi, folks. Guess who's in the kitchen with me? John Hutchison. And we're gonna make power cells. Power cells.
Oh, hello Carla. How are you doing today? Great to see you again.
Someone's in the kitchen with Carla. Someone's in the kitchen, I know. John, what are you doing now?
And today we're making power cells, really.
What is a crystal power cell, John?
A power cell, Carla, is a energy collective system. Picks up ambient energy and converts it into usable power.
Oh, really?
You know, I read about making power cells by T. Townsend Brown a long time ago. T. Townsend Brown took minerals and found that they give off electricity. I tested certain minerals to see what kind of voltage readings I get off the minerals. So I read about T. Townsend Brown's work and decided to do some experiments. Well, the first experiments I did was for a group of business people to make a power unit that's non-moving part technology, and I did so. Using barium titanate cylinders I bought from Federal Radio Sales that give off their own natural power.
Oh, John, you're using Rochelle salts, and why not Carla salts? I am very salty. Can be quite salty. And, people told me I am electrifying. Quite electrifying, and sometimes even a little over electrifying.
Well, can't use Carla salts, but Rochelle salts, I actually read about those in many books for a long time. And they were used for making crystal microphones and other power generating stuff.
Why do you use Epsom salts? I used it one time and, ooh, that was painful.
And recently, using what you're holding here, Epsom salts, we add that to the Rochelle salts and get a unique crystal formation. Simplistic technology, really. And also we found that the Epsom salts increase the power. Well, Carla, the Epsom salts work with the Rochelle salts in a symbiotic relationship, creating a little bit more power. So I use Epsom salts in some of my creations of power cells.
Sodium silicate. What are you going to do with that? I hope you're not going to drink it. Ooh. John, why do you use sodium silicate?
And sodium silicate has been used for making power cells. And it's a recent introduction about a couple of years ago into the mix as well. The sodium silicate, when it dries out, it forms crystalline structures which are compatible to the Epsom salts and Rochelle salts.
Oh, what is that and what does it do? Looks like a little crocodile to me, but this looks like a nail file. This looks like something, I guess something.
In making your power cells, you're going to need a small file like this for the doping agent. You want to file off some small amounts of it off the galena and iron pyrite. You'll need this to hold maybe this here like so, or grab other small items to form it. This here you can use for crushing or holding hot items when you're making your power cell. And most important, of course, is your volt ohm meter, so that you can take readings of the voltage and milliamps that you get from your power cell. We have here a small cylinder where we're going to be putting the mixture in, and in the center of the cylinder we're going to put a small thin piece of metal inside that to act as a positive. And what Carla forgot to mention is we use tiny amounts of doping agents like iron pyrite. We use doping agents in small quantities like iron pyrites and other minerals like galena to add to the rectification of the voltage inside the power cell. And Carla forgot to mention, of course, the power supply, which is 12 volts DC, and what we do is apply, after we heat up the substance, we apply a small amount of direct current to the power cell to polarize the elements inside, and then take the power off, and after that it's self-reactive. So in this particular case you need a small ladle because we're going to be making just a small power cell, and you only need, instead of a large container, just a small ladle like this to put your mixture in when you heat it up, and then you pour it into the crystal power cell. And you can heat it up directly on the stove. Be careful, you don't want to heat it up too hot. I have decided to open source all my technology. I've taught Nancy, and Nancy will now teach you how to make a power cell.
Tonight I want to discuss with you the bounty that we have here in this country. The meal that we partake in that has been built by actually the blood of our ancestors. These are our rights, our liberties, our freedoms. We all come to the table at this country, and we're going to partake of those things that have been established here for us. They were established and set forth in what's known as our constitutions. Our constitutions are a compact. A compact is a type of a contract between us on how we live together and how we're going to create a government that serves us. Not that we serve the government, but the government serves us. The problem is that as we come to this table to eat and partake of those things that have been built for us, it all comes with a price. That price is that we fight for each other's rights. It means that when somebody in this compact, this constitution that we created, when their rights are violated, it requires that somebody else in the compact, which means another citizen, which means all of the other citizens, that we have to come and fight for that person. The problem is, a lot of people are coming to the table and trying to eat, but they've never actually come and put anything onto the plate. All they do is they come and they want to eat, but they're not willing to fight for you. They're not willing to fight for me. What they're doing is just taking from us. And who are those people that are actually taking from us? Well, folks, they're the citizens that sit and watch this show and they think, oh my goodness, I'm so glad that somebody is fighting for our rights. But then they're not willing to fight themselves. All they want to do is come and consume. Well, I've had enough of these folks. I've had enough of the people that say, oh, our rights are being violated. but they're not willing to do anything. They're not willing to fight for those rights, and they're not willing to fight for your rights or mine. Come to the table, have my food, pour myself a glass of wine. In fact, maybe I'll drink the whole bottle and get inebriated, because it's getting really tired out here, folks. There's so few people that are willing to put in to create the plate of food and to protect the rights of everyone.
See what you're doing.
Okay, let's make some crystal power cells. And we start with Rochelle salts and Epsom salts. Now, Rochelle salts are made from cream of tartar and baking soda. And there are recipes on the internet on how to make your own Rochelle salt. When we weren't getting Rochelle salts, because we've bought it off of eBay, and sometimes they have it and sometimes they don't, we've been able to use the cream of tartar and the baking soda and heat it along with the Epsom salts, and we still do get a power cell. Not quite as strong, about 10% less in power than the Rochelle salt when we get it directly from a manufacturer. So if you can't get the Rochelle salts, go on the internet, look for a recipe for Rochelle salts, and you use cream of tartar, organic cream of tartar, like from your co-op, and you can get a bag of it, and baking soda. So I'm going to take 1 part Rochelle salt and 2 parts Epsom salt. I'm going to put it in this glass container here because that's what I'm going to use for mixing. Now, we're going to only use a very, very small portion of our mixture, but I need to dope it. And we only use a very, very tiny amount of doping in the power cell mixture. And so since I'm going to be only making 1 tiny cell, to be able to do that with the doping is a little bit difficult. And this way I have extra materials for making more cells.
So let's mix it up. Let's make some cells.
So we're going to take 1 portion, this is just a 1/4 cup measure, it's a little bit less than a 1/4 cup, and we put it into the container. The Rochelle sometimes will come lumpy. If it comes lumpy, just pull it up and just squish it with your hands, because you want it smooth, because we're going to try to make as smooth of a compound as possible.
Epsom salt, Epsom salt. Look at this, Epsom salt. Woohoo!
We're going to smash it down so it doesn't have the lumps in it. Okay, 1, 2. Go get a spoon and mix this up. Get that incorporated as much as you can, just like you're cooking. All right, now our doping agents. We've got calcium carbonate, and we're going to take that crystal, so you can see there's this fine powder that's coming off. This is a silver medallion that's 99.99% silver. You have to be careful with this, especially the smaller cells, because your cells can short out by having too much silver or too large of a particle of silver in. Iron pyrite, also known as fool's gold. So how do I know how much to put in here? I don't know. I've made hundreds and hundreds of these and experimented with various compounds to put in. And this is our little magic piece, which is galena. Normally you're not supposed to hold this with your hand because it does contain lead.
Why do you need that?
And galena acts as a radio receiver. I can look in the top and see the galena and the other compounds on there. Now I'm going to wash this and wash my hands and be right back. Drying off the file, my hands. Make certain that your hands remain clean. You don't want any contaminants on your hands or oils. So we're going to put our doping agents off to the side. Take a look here. And again, we want to stir, stir, and stir. Quite a humid day today, and so the salts are kind of clumping. That could cause some problems in heating. You have to be extremely careful about the moisture. Now I'm going to put these off to the side, and we're going to prepare the actual components of the cell. Normally this is enough for approximately 30-40 cells, because the cells are only going to use about this much of the compound, one cell. What we've found is that the smaller the cell, the better it works. Everything happens right on a microscopic level. And I've taken sodium silicate now. I put a little bit in this glass. Sodium silicate, we've bought this directly, but you can also find it in the auto parts store. Okay, this is one of the products that has the sodium silicate in it. As you can see, we've used it. What we've done is we've poured it off the top. Sodium silicate is right here. And if you can't find just the regular sodium silicate, this is a way of getting sodium silicate. So I've poured some of the sodium silicate off to the side. This particular sodium silicate is quite thick. It originally was low moisture content, and then we let it evaporate some. And there's a reason why we don't want the moisture, is that we don't want the chemical reactions happening due to the water. So I'm taking this piece of galvanized, very thick galvanized wire, and I'm gooeying it into the sodium silicate. And what we're going to do is this is copper tubing, so we have different metals, not like metals. You can use two like metals, like silver and copper, but we found that different metals work better. Now see, I've got this little piece of the sodium silicate coming in here. What I want to do is get in here and create a coating of the sodium silicate. The coating of the sodium silicate is going to do a couple of things. One is it's going to act as a glue, and we found that as these cells will over time dry out and actually grow, the crystal structure grows, they will pull apart from the metal. And having the sodium silicate on here acts as a glue. As well, it facilitates the crystalline structure. It becomes part of that and part of the energy. Because this is so small, I've got a block here to put it in, and I'm going to put my other piece here and block it in the block as well. Clean my hands again. One of the important things on the cells, especially the ones that are made out of cylinders, is that the back end of it needs to have some type of a plug. And in copper tubing, we found that a simple Q-tip works, especially if you can take and compress the cotton up to the end. And you place that in the bottom and then clip it. Okay, so now this has been prepared. It's going to be sitting here in my form and ready to go. John mentioned about pouring into the cells. We found that with the smaller cells, it's very difficult to pour it in, so we'll show you the other procedure that we're using. So we're going to put this off to the side, and we're going to move over to the stove. The fly swatter is there because we don't want any organic material, and I do have a fly that's been running around, so he's going to be here just watching us. So this is going to be a two-handed kind of an event here. I'm going to be putting the compound into the ladle. Move that out of my way. This will be heated up, and then I will need to take my piece of wire. This is the galvanized wire that's been coated in the sodium silicate. And once this is heated to the correct level, I'm going to spin it around inside of here and then place it into the tube. And we'll have actually lots of extra compound. So I'm ready. It's two-handed. Let's start the stove. We're on a medium heat. The Rochelle and Epsons are just starting to melt. Almost there. As soon as it clears out there, almost there. Okay, that's about it. I'm going to swirl this in. And we go into the cell. Now as we notice, we've got some of this coming out. We're going to try to move it into it as much as possible. Come down. Come back for a little bit more. There she goes. Right there. That little blob in. And push down. Pushing with your thumb on the plug. And we're going to put this into the form. All of this is water soluble, by the way. Push into the form. Now, let's check and see if we are at power. We have not put the charge on this yet. We're just checking and seeing where we're at and making sure that we're not shorting out, because we have a very, very, very slow, very small tolerance on this. Generally, the inside is our positive and the outside is the negative. Except this time it's the other way around. So right now we're showing 0.748 with the outside being our positive and our inside being the negative. Well, this even likes it even more. So we're dealing with heat right now. We're dealing with any moisture that might be having a chemical reaction with especially the copper. And what we want to do is just give it a short little hit with the power source, and by doing so we're setting up the alignment of the crystals, and then we're going to let it rest and see how she does. Take our leads and just slap them on here for a second. There we go. It's easier. Coming off at 1.6, 1.59, so it's going to settle down. All that's doing is just setting up information to the cell as to how it's supposed to be sending its charge. Okay, we're going to go back to the stove and I'm going to show you what you don't want to have happen. This is what happens when you go too far on your compound. Is that, see, we have this nice taffy and we're able to work with it. And notice the white that's building around the edge. You have gone too far when you have a pan full of white or a ladle full of white. You can kind of recover it if you're spinning it around, but very shortly you will see that the Rochelle and Epsom doped mixture will become solid white. It will become difficult to work with, and it will not be effective as a power cell. So you see how white everything is getting here. You do not want to go that far. It's not a good thing. So this is how we make crystal power cells. And we have made hundreds and hundreds of different crystal power cells. Let's look over back at her cell and where she's sitting at now. She's going to be settling down. Generally what they do is they settle down to their voltage that they were before you put them on the power supply. The power supply gives them a boost of energy. All we want it to do is line up the crystalline structure, and we generally will end up with something around 0.5, 0.7 volts on something that is this size.
I like this free energy thing. Do you?
People say, what is your amperage? Well, your amperage is going to vary wildly, and it's determined by the shape of the cell. The flat cells, which we'll be showing some of those, that you can actually build between pennies or between different pieces of flat metal, are going to have voltage but extremely low amperage. The ones that carry amperage are going to be your cylinder sizes, the cylinder shapes like this one here. Check the amperage on this. Well, this guy got a nice little shot coming off of, with 7 milliamps off of the charge. You will not maintain that. I am very definitely sure that they will not, this is coming from the charge that they've gotten their amperage. The key thing is to make sure that they are properly made in the first place so that you don't have a lot of moisture and thereby you don't have a lot of that chemical reaction going. You want them to dry out, and I've usually given them a little bump like we just gave on this power supply after they've dried out. Once they've dried out and I've given them a bump, that generally means that's the power that they maintain. And then it's also very important to put them on a load. And finding the particular load is difficult because you have to have a series of these in order to have enough to actually power something. And you need them made identical. You need to have all your standards down because they are very particular, the cells are very particular in when they work together in series or parallel that they're exactly the same.
I love what you're doing. It's awesome. Free energy for everybody. Woohoo! Yes, even Carla can have a free energy device.
Now we have some extraordinary power cells that are not these little cylinders, but they are totally different forms. They give off AC and DC current at the same time, and one of them actually created a force field, is all I can say it was, and I'll show you that in a clip later, and mutated and melted a bunch of aluminum. So these are extraordinary pieces of technology, very simple to make, and they really are our way of breaking free of the power grid.
You just gotta love it, boys and girls and children and hobbits and old folks that haven't really grown up. Oh well, you know what they say. I forget what they say, but they said it anyway.